Hello, students. Today we're looking at the zero's the hero. Hero.
I thought Mr. Carlson was the hero. I almost said Mr. Butterworth. That'd be very self-centered. Mr. Carlson was the hero. Goodness,
To be fair, I thought you were getting us confused, which I know happens.
it
Uh,
is true. We are basically the same person.
it's true. Okay, so I see in the warm-up we've got to determine the possible values of x in each function. And I noticed some stuff that looks like things we've done before, where we have things that are multiplied together and we have to figure out what would make that whole thing equal to zero. And all of these are equal to zero, which I think is an important thing.
So the thinking that the student should do right now is what equations or what additional
Mm.
equations would I have to write for these various questions? And some of them might not need additional equations, but you might need additional equations for some of these. And you should be thinking, or feel free to pause and like actually do write down some equations that you know you're going to have to solve.
I think that's a good idea too. Uh, do we want to go through them now and talk about what we would do to set up some of those equations now that they have paused and come back?
Yeah, I think it might be helpful to write down the various equations that
Hmm,
they should have written down, and then give them another opportunity to make a good decision and pause the video and solve those various equations.
I like it. So I'll do number one. For number one, the equation that I can get from this is a really tricky one. It's going to be 2x minus 5 is equal to 0.
That was profound, buddy. That was
I know.
profound.
And the reason that I just wrote that is because I don't have anything that I'm multiplying that makes it hard to kind of see this linear term to solve for x with. I'm going to do number two also
Ooh,
because
getting bold.
I'm feeling kind of spicy. Uh, and I'm going to say that x plus 4 equals 0. And I'm going to say that x minus 4 equals 0. I left those in parentheses. That's not a necessary thing to do. But I find that sometimes that helps to see that that's the unit that we're moving around and that this kind of that thing goes together and not just x or not just the plus 4.
So you've done two of them. So that means I got to do those. Now, did you do for number two? Did you do that because you had two things multiplied together and you got zero as a result? So your choices are one is zero or the other is zero.
That's correct. We've talked about this something called the zero product property in the past.
So does that mean for number three, I should write x equals zero? And I'm not going to use parentheses to show them that it doesn't matter. X plus 3 equals 0. Those would be my two equations for number 3. And then similar argument for number 4. Number 4, you'd have x minus 5 equals 0. X plus 1. I was trying to do more work there. X plus 1 equals 0. And x minus 2 equals 0.
Um, Now, Mr. Butterworth, one of the things that I noticed that in writing these equations, it didn't really matter in terms of difficulty whether we had only one piece or two pieces or three pieces. Kind of the work is still the same. And all of these equations are really easy for us to solve right now. And we've been doing these things like this for a long time. Should our students be solving these equations now?
That would be great. You should pause the video and solve the equations.
Do you think they did it?
I think some of them that really want to be successful did. And I think some of them that now feel bad are going to pause now. And
Okay,
others just aren't. And that's okay. So let's go ahead and I don't think we need to talk through the solutions here. We can just write down what the answers are. I'll start at the bottom.
I'll start at the top.
I hesitated at that one on number 3. It said x equals 0. And I was like, but it's done. So I don't got to do anything there.
So you mean I wrote that for nothing?
You did, you silly
Oh,
goose.
all right. So now we're talking about this characteristic of polynomials that we call degree. And that's basically kind of like the family that a polynomial fits into. So we've talked about linear equations. We've talked about quadratic equations. Now we've talked about cubic equations. Those are all part of a larger classification called polynomials. And we categorize those by the biggest exponent that they have, which we have another name for, and that's the degree. Something that has 1x in an equation that's not multiplied by any other x's, that would be a degree 1. And you can kind of shortcut this by thinking about, I just meant to draw a line down.
Oops. You distracted me with what I was doing.
I know. So if x to the first would be the highest power, that degree would be 1. If x squared is the highest power, that degree would be 2. And if, I don't know, x to the 7th is the highest power, that would be degree 7. Sometimes this is kind of hiding a little bit. So if I'm looking at something like h, I know that if I were to multiply this out, x times x there would give me an x squared. So we'd say that this is degree 2, even though it doesn't look like that based on how it's written. So we have to be a little bit careful with that. Similarly, for something like e, we've got x, and then it's going to be times an x and times another x. Because we have 3 x's multiplied together, even though we have some other stuff we have to distribute there, that is going to be an x cubed, so that would be a degree 3. So we're really counting the x's that we're multiplying together.
So is it fair that it would be a good idea to pause right now and for you guys to try to do A, B, D, and F? I did put in red there, kind of, if we multiplied things out, some various, there is like an infinite number of ways of writing these things, but some various ways to write linear, quadratic, and cubic functions. So you should pause and you should try to do A, B, D, and F.
And we're just looking for the degrees here, so they don't actually have to multiply these out sometimes, right?
Correct, just
Cool.
the degrees. Now that you've paused, hopefully now you've unpaused. Mr. Carlson, you were just talking about like in E, you had X and then another X and then another X. And if you multiplied that out, you'd have degree 3. Is it fair to also say, given some of the stuff we've gone through before, is we have kind of one linear function, another linear function, and a third linear function?
I think,
So
yeah,
if we
it's a
have
really good way to think about that.
3 linear functions makes a cubic. And then in this one, we have one linear function, another linear. So we only have 2 linear functions there. So that's a quadratic.
Yep.
So we can
I
think
like
of
that.
it that way.
The dogs agree with that too.
I knew Winston had my back. So the first one would be degree 1. Second one would also be degree 1. Third one would be degree 2. And then the last one would be degree 3.
And that's because, again, we can count 1, 2, 3 x's that we're multiplying together, or 3 linear functions that we're multiplying together. All right, so now we're taking kind of what we did at the beginning and adding one more piece on it, and that is this word multiplicity. And Multiplicity is not just a wonderful 90s movie starring Michael Keaton. Is it Andy McDowell is the?
I think so.
Wonderful movie. But it also is a really important idea in algebra. And we saw some of this happen when we were looking at zeros and imaginary numbers, because we had some weird things happen. Like if we had x minus 1 squared, one of the things that we noticed was that it just hit the x-axis and didn't pass through it. This is going to connect to this multiplicity idea and kind of why that happens. Because here we have, and we actually have the same function here, one linear term, but 2 copies of it. And that's a really good way to think about multiplicity. So we'd say that this factor has a multiplicity of 2. I accidentally hit the eraser. There we go. If I had that cubed, that would be a multiplicity of 3. But here they're talking about something else. They're talking about the zeros and the multiplicity of those zeros. So I was talking in terms of the factor. What does that mean in terms of the zeros?
So if we have a factor that shows up twice, like x minus 1 squared, if we think about what we did on the first page, wouldn't that mean we write down x minus 1 equals 0? and also x minus 1 equals 0, and we
Oh,
solve those two equations?
so it's the same equation. That equation just happens twice, which means that that 0 happens twice.
Right, so then you get x equals 1 and x equals 1. So that means there are two zeros, but they're the same number.
So in looking at D, which this one really is, so you got x equals 1 as a 0, but it happens twice. So we could say that has a multiplicity. I'm writing that out instead of just writing mult, 2.
Yes. Now, obviously, you don't have to write the same equation down twice. That's kind of silly. But if that helps you to process what's going on, to write it down twice and say, wait, it shows up twice, that's totally fine. It is up to you. So you should probably pause right now and see if you can find the zeros for the other functions and determine if they show up once or twice. I'll give you that hint. Those are your only two choices in these examples.
So no,
Once
no thrice.
or twice. No thrice.
Okay. All right, now that they paused it, let's maybe take a look at a couple of these. I'm going to take a look at E, because I think that that's nice, could have some different stuff going on there. And I've got x equals 0 for the first part. And then I've got that same thing happening twice. So I'm going to write that as x minus 1 equals 0, which means that x equals 1. So I've now found my zeros. We also have to say what their multiplicity is. That one only happens once. So that's multiplicity 1. This one, there are 2 copies of that. So if I had done both equations, and again, if you'd like to, if that's helpful to you, cool. If you want to be more efficient and just write that once, that's okay too. It doesn't matter. But since that one happens twice, that would be multiplicity 2.
So can I run with that idea when I look at f? Because I'll have the same factors. I have a factor of x and a factor of x minus 1. So my equations, once again, are going to be x equals 0 and x minus 1 equals 0. X equals 0 is already done, but that one showed up twice. So I can write multiplicity 2 for that one. And then that's x equals 1, but that one only shows up once this time. So that's multiplicity 1.
So these two functions are similar, but they have like their zeros switched in terms of their multiplicities.
And it might be an interesting adventure for, we might do this later, but if you wanted to go to Desmos and put k of x and m of x in there and look at what's going on, it'll give you a preview of where we're headed. And you might be able to draw some conclusions about what's going on.
I wonder if that would be a good starter for their in-person day.
Oh, maybe.
All right, and there's another question down here. What do you notice about the zeros of this function counted with multiplicity and so combining these with degree? Well, let's take a look. So for the ones that we did, E is going to be 1, 2, 3 x's. I'd call that degree 3. And I got a multiplicity 1, I got a multiplicity 2. If I add 1 and 2 together, I get 3. Huh.
You do that for f also.
Oh, because we've got
an x, and then an x minus 1. So that's degree 3. And then 2 plus 1 is 3.
So the sum of the multiplicities is the same as the degree, which is kind of a weird way to think about that.
For D, we had multiplicity 2, and that's a quadratic, so that's a degree 2.
Yeah, that makes sense.
And for the one before that, we didn't do it, but each of those only shows up once. So 1 plus 1 is also 2. Ooh, I think there's a pattern emerging.
Yeah, some kind of fundamental pattern.
I
couldn't help myself.
I know.
All right. So what we're going to do next, and we're going to do a couple different decomposing activities based on different families of functions, is we're going to look at kind of building and breaking apart a quadratic function to kind of see how that's built from zeros and how that's built from linear pieces. And we've done some of this before, but now we're going to do this in a more deliberate way.
If you don't know what decomposing means, you might be thinking about like bodies breaking down or something. Yes, it's breaking things down into their pieces. So this is breaking a quadratic function down into pieces, which if we look at the graph, those are 2 lines. So breaking a quadratic down into 2 linear functions. which is what it says in the words there. This function was written as a product of two linear functions, because this is from that rain gutter thing.
The rain and plane falls mainly on the Spain.
Yes, exactly. Very
Okay.
good, Pygmalion. So we have y equals x, or h of x equals x, which they labeled for us, and then negative 2x plus 8.5, which is L of x, which they also labeled for us. And they want to let's do
That's
things
weird they
without
chose that and made it cursive.
for the L.
Yeah, because
It's
the eight.
because it's
Yeah.
the length. But I agree.
All right. So I see our lines, and they also tell us that these dashed vertical lines break this up into some specific regions based on where we have zeros in between the zeros.
So it says label the zeros of each function with open points on the coordinate plane and on the number line below. So does that mean they want us to do like an open dot here and an open dot there?
I think so.
Okay.
That seems to be the way that that's being phrased. So I think that's a pretty good way to do that.
Okay, I'll read what's happening next because we can't see it, but we're going to need
Okay.
this picture. So next it says determine whether the output values of the product h times L is positive or negative. Label the number line accordingly.
All right. I know for region A, H is negative, L is way up here, so that's positive. Product is multiply, so if I multiply a positive times a negative, that would give me a negative value.
So you're saying h was less than 0, L was greater than 0. A positive times, no, write it correctly. Sorry.
Yeah.
A negative times a positive is a negative.
Yes.
Got it. So then we want to do that for the middle region. So for the middle region, I can see that L of x is positive and h of x is also positive. I'll color that so that you can see what I'm talking about. Those two are both positive. So in this case, they're both positive. So that's a positive times a positive, which is still positive.
Cool. So that middle part's going to be positive. And then for region C, h of x is positive because it's above the x-axis. L of x is negative because it's below the x-axis. And we already talked about if you multiply a positive times a negative, we get a negative value. So this third number line region is going to be negative down here.
Now, if you're super confused right now, maybe look at specific or estimates of numbers. So if I look in region A, if I take like a point right here, which I'll call a y value of -4, and if I take a point up here, which I'll call a y value of 12, no idea what it is. If I do -4 times 12, that's a negative number. So that's why we put right here that we would get a negative number, because we're saying for any points we pick, if we multiply those y values, we get a negative value. Similarly, if we pick something in that region, maybe 3 and 3, 3 times 3 is positive 9. Anything we choose in there, any set of y values we pick in there, we're going to get a positive. And then same idea over here with the negative. There's an additional piece. Oh, that's what it just said. Choose an x value in the region. Evaluate the functions for that x value. Plot each point. So now we want to come up with some points.
Would it make sense to build like a triple table?
Yes.
X. I'm going to write the equation. Oh, h of x is just equal to x. So I'm going to just put x there, and then L of x is -2x plus 8.5. Okay.
And so if we choose an x value in the region, I'm going to choose -1.
And that's in region A.
Yes. So h of x is -1. And then L of x will be 10.5.
So if I were to plot these points, what they're asking for is the x, y. So -1, -1. That's there. Do we plot the points or are we plotting the
We plot the
product?
result, the product.
So I don't need to do that.
Correct.
There we go. So I need another thing that's the product over here.
I'm putting that over here just to
Cool.
give us some space. H of x times L of x. So I got rid of all the directions. When we plugged in -1, we're getting -10.5. So we're getting something down here.
We had to choose the one that's going to be immediately off the grid, which, to be fair, I think any number we had chosen for that would have been that case.
That's why I chose as small an integer as I could.
That makes sense. Okay, so if I choose one in the B region, I'm going to choose 2, just because that's kind of square in the middle there, and 2 is a pretty nice number to plug in. H of x is going to be 2, and L of x, that's going to be -4 plus 8.5 is 4.5. So when
So
I
if I multiply
multiply,
those together, you get 9.
you
We
get
were saying that at the same time.
that's creepy. So we get 2 and 9 right up there.
Okay. And then if we go for the last region, let's again pick something relatively close. So let me plug in 5. So if we plug in 5, the first one is 5. And then the second one is, that's going to be -10 plus 8.5. So it's -1.5. So if we multiply those, we get -7.5. So 5, -7.5.
5, -7, -7.5. All
Let's
right.
see. Now they want us to sketch it, basically.
I mean, we also know that at the zeros, 0 times the other function is going to be 0.
Mhm.
I'm going to erase that little scribble because it confused me. So if I'm sketching this thing, I'm going to sketch this in yellow so we can see it a little bit clearer. It looks like we're going to go up. We're going to keep going up. I don't really know what's happening around that, so I'm just going to start going down from there and keep going down. And that looks roughly like a parabola to me. It's not exact because of the points that we chose, and especially because one of the zeros is at 4.25. So the vertex would be at 2.125, and that's kind of awkward.
Yeah, remember in a previous video, we talked where the vertex is going to be. So it'd be a little bit above that point we picked at 2. But that generally looks like a parabola that goes down. Now we knew down here on the left, we knew we would keep going negative because we were taking bigger and bigger values and multiplying them together. And then the same idea here, we knew if we picked points out here, those would be bigger and bigger values. And so that would make bigger and bigger negative y values over there.
So even though we see this point, that's one of the ones we figured out, going beyond that, it is going to keep going. And that the reason is for what Mr. Butterworth was just saying.
Right. So I think now we can just start going to the next page and just talk through it again to reiterate what we're talking about. So we broke it down into those 3 regions. We determined whether the values were positive or negative by looking at the y values of the lines. And we labeled the number line, and the number line wound up as negative, positive, negative, with 0 here and 4.25 here.
And so the numbers you're using, this is talking about the y values, and this is talking about the x values down below.
Yes, that's important to keep that in mind because that gets confusing.
It does.
And by y values, we actually mean, hi puppies, h of x times L of x is what our product is. And then we looked at specific numbers. That's what they asked us to do. And then if we go to our next slide, they're going to ask us to describe the product when things intersect. So that's, again, just a specific point. And then talk about the zeros. If either H is 0 or L is 0, then the product has to be 0. So that's why when we had our graph, we had a 0 at 0 and a 0 at 4.25. And then we took all that information and we sketched that graph, which again looks something like this. Sorry about the weeble wobble at the beginning there.
I think it looks
And
lovely.
then the last part says, how does a zero product property relate to the x-intercepts?
I'm going to take a stab at this. So we talked about the zero product property. If you have two things multiplying together, the answer is 0. One of them has to be 0. Here we have three functions, one of which looked like the parabola that we drew. One was a line going roughly like that, and one was a line going roughly like this. Since the parabola was the product of these two lines, and there were places that these were 0 for the lines themselves, those are also going to be zeros on the parabola because one of the things being multiplied is 0, so the answer has to be 0.
So is it fair to say that if they break something down into these linear functions, which is what it seems to be doing, the easiest points to pick are wherever those linear functions hit the x-axis?
I think that's fair.
Because those will show up on the function that we're creating.
Mhm. Oh, look, we have more lines for them to look at. So this looks like we're being asked to do the same thing, where we've got P of X is the product of these two lines, and we're asked to find some pieces of this thing.
So I think it would be good for you to pause the video right
mm,
now and try to do this. Try to identify what the shape of this curve is going to look like. Try to figure out where the zeros are. Try to figure out where the y values are positive, where the y values are negative, and go from there. Obviously, we're going to do it for you, but if you pause the video, you're doing your job and you're thinking ahead, which is really important. If you're just thinking with us, that's good. But if you're thinking ahead, that's really going to get it in your brains there.
True.
Oh, and it says predict the function family of your sketch before you get started. So we have two lines. We're multiplying those together. You should be able to tell us whether that's going to be a linear function, a quadratic function, or a cubic function, because those are the only three that we're talking about right now. I'm going to hope they paused and did some work. So I think we can go now. So we've got sketch the graph of P of X if P of X equals S of X times V of X. Okay, I'm going to say easy points to pick are negative 2, 0, and 0, 0. Those have to occur on P of X. Then to the left of negative 2, maybe I plug in negative 3. And if I plug in negative 3 to V of X, well, I'll do S of X because Mr. Carlson has that first. If I plug in negative 3 to S of X, I get negative 2. And then if I plug in negative 3 to, sorry, not negative 2, negative 3. If I plug in negative 3 to V of X, I get negative 1. So S of X is negative 3, V of X is negative 1. So the product is 3. So I just plotted the point negative 3, 3. If I pick something in between, maybe negative 1, if I plug in negative 1, S of X is negative 1, and V of X is 1. And then negative 1 times 1 is negative 1. And then if I pick something to the right, maybe 2. So if I plug in 2, S of X is 2, and V of X is 4. 2 times 4 is 8. And we have our curvy curve. You didn't need to sketch it. So this says sketch it. You don't need to plug in specific numbers. If you just want to sketch, your sketch would just be, okay, it will look something like this. Oops, I missed. Just make your dot bigger if you missed. It's fine.
That looks wonderful.
Because you're just estimating. That's all you're doing.
And in terms of a sketch showing important characteristics like x-intercepts, Y-intercepts is really important. General shape is really important, but getting lots of points accurate, not so useful. All right, so looking at question B, identify the x-intercepts, explain the relationship. So we have the x-intercepts. The x-intercepts are at x equals -2 and at x equals 0. And we got those because when we multiplied those things together, we got 0 as an answer. And that's came from each of the things we're multiplying, which also had 0 as a value at those places. So I think what this is saying is that the x-intercepts of the lines were the same as the x-intercepts of the parabola.
Then it says identify the vertex. Well, if we've found the x-intercepts, the vertex has to be in between those x-intercepts because this is a parabola. They're symmetric. And we actually found it. It was -1, -1, because that's halfway in between -2 and 0. So the vertex is -1, -1.
I like it. Ooh, decomposing cubic functions. I wonder if we can do the same thing, but different.
I bet we can. And I bet I'm going to predict something. I bet if we make a cubic function out of all of these, this is those volume ones that we talked about in a previous lesson. I bet the cubic function is going to have these points on it. This is going to be my guess.
So you're saying like we found the zeros for the lines were the zeros for the parabolas, and you're thinking the same thing might be true here.
Yes. And it says we want to sketch using our brains and not technology. So we're going to, on the next page, break this down. So we don't have to break it down on this page.
So maybe not think about this in terms of exact numbers, but more positive, negative type things.
Yes, which is what they're asking us to do on the next page.
So if we have these 3 0 points, and that's how we broke up the last one, does that make sense to break this up into regions as well?
Yes.
And the other thing that I notice is that I can pretty clearly see whether pieces of this are above or below the x-axis. So I'm going to do something kind of wacky. And here I'm going to just like write the signs of these 3 lines in each of these places. So going from the bottom up in the first region, we've got a negative, we've got a positive, and a positive. If I multiply those 3 things together, negative times a positive times a positive, I'm going to get a negative as my final answer. For the next region, I've got a positive and a positive and a positive, which gives me a positive when I multiply them together. For my next region, I've got a negative and a positive and a positive. So negative, positive, positive. We said that was a negative value when we multiply those. And then for my last one, this one's kind of tricky because I almost lose this line here. We've got a negative and a negative and a positive. We know that if we have 2 negatives multiplying, that turns to positive. Times a positive would give us a positive value.
And if you're confused about how Mr. Carlson's coming up with a negative, positive, negative overall, if you think of it as just like -1 times +1 times +1, and your job is just to figure out is that a positive or a negative, that might help. If you're confused about where Mr. Carlson's getting the initial negative, positive, positive, that is based on the y values of the region. So negative, positive, 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 negative, positive, positive, negative, negative, positive.
All right. Do we want to keep this open? Have you asked questions again, or do you want to move on to the next slide?
The next slide is going to be continuing this. We might as well just use this slide. So they asked us to draw the vertical lines, which we did, determine the output values, which we did. And then how do you know where v of x crosses the x-axis? That was my assumption at the beginning where I put those blue dots. And my assumption is because we have that product, if any of those are 0, then the overall function has to be 0. So we had to have a 0 at 0 and at 6 and at 9, which we already saw in our previous week. And then it says choose an X value in each region, evaluate and determine the product, plot each point. I don't know that we necessarily need to do that. I think we can go ahead
Yeah,
and just graph, because I think that's going to be more useful for the humans. If you want to pick specific values and multiply them, by all means do it.
sure.
Part of my hesitancy is if I look at this first region we have, if I pick like
Any point.
-1 to plug in, I'm going to be multiplying 200 by 140 by some fraction. That's going to be off my graph. So that's kind of a useless exercise. But the important part is we're going to be negative. So if we go with the yellow idea Mr. Carlson said, we're going to be negative, then we're going to be positive, then we're going to be negative, then we're going to be positive. So we're going to look something like that, which if you remember from our previous videos, that's what the curve looked like.
It is.
And we didn't have to do that much work to get it.
All right. We just talked through all these. I don't think that we need to talk about those again.
Correct. I think they'll be all right with that. And now we have the same idea, but the next function we talked about, which we talked about an area function, which was pi x squared, which that's just a quadratic, pi x squared. Ignore the pi for now. That's like saying x times x. So if we set that equal to 0, we would say x equals 0 and x equals 0. Now, the reason I could ignore the pi is because it was really pi x times x. But divide both sides by pi, and it's just x times x.
It's true, because pi is just a constant. And we know it's about 3.14. So it's a little bit more than 3, and that's really about all we need to know for this. Would it be fair to kind of sketch this graph? Because I know that if x equals 1, we're going to have pi as our value. And I think that that would be a good point to plug in on this graph. So if I've got 1, I'm going to go a little bit above 3. And then -1 times -1 would also be 1. And we're going to see the same thing, which hopefully is not too much of a surprise, because an x squared is a parabola. We know that parabolas are symmetric. And this would be something that looks roughly like this.
And I added that term multiplicity 2 to reiterate what we have previously talked about. You missed.
Yeah, I have a dog moving my arm right now, which is really fun to try to draw with.
There we go. All right, and then the other function is 2x. So that's y equals 2x. So if I have h of x equals 2x, if I set that equal to 0, then my equation is 2x equals 0, so x equals 0. So that will go through that same point. And then if I channel my inner Algebra 1 student, the slope is 2. So go up 2 over 1. Be careful of the scale because the scale is wacky.
I was going to say we got to be real careful with that here.
Because it doesn't look like I'm going up 2 over 1 because the scale they picked. But that's my graph there. I went up 2 on the y-axis and over 1. And then we got to build a cubic. So the point, we know one point.
We do.
Hopefully you guys can predict what that point is. Hopefully you're saying it in your brain right now. The point that we absolutely know.
I'm trying to read their minds through the videos, and I don't see them saying it in their brains right now.
Shout it out loud. You can do it.
Oh, okay, I heard it that time. Okay, good.
So it's going to be here at 0, because that's where a of x had its zeros. That's where h of x had its zeros. In fact, to connect this to the beginning, that 0 has multiplicity 3.
Ooh.
Because we had multiplicity 2 right there. We had multiplicity 1 right there. We're multiplying these together. So now we have multiplicity 3.
All right, I'm going to go one step further and take a look at the sides of this. On the right side, both of these are positive. So if I multiply those, I'm going to get a positive value. On the left side, 1 is negative, 1 is positive. If I multiply those together, I get a negative value. So to the right, my graph is going to be positive, and to the left, my graph is going to be negative. There's some more complication about the shape of this graph, But I'd like us to remember that when we were looking at cubics, we had two different shapes of graphs. One looked like this. That doesn't seem to be what applies here because we'd have to cross 3-ish times to kind of see something like this. And I don't think that's what's going on here. Especially not since we have going from negative just to positive. The other one looked like this. And this shape fits really well here because we've got a spot in the middle that we call a point of inflection. When we've got stuff to the left of that that's negative and stuff to the right of that that's positive. So I think that this would be a good example of this type of shape.
How'd I do?
That looks wonderful.
So there's this thing called the fundamental theorem of algebra. We're not going to talk about it that much. Basically, it links the degree with how many zeros there are. That was what Mr. Carlson and I were talking about at the beginning. Not a big focus for us. So, but if you want to talk about it, we are happy to spend some time talking to you about it. But we're not gonna really hammer that right now. I love this. I just love the structure of this. It's beautiful. So
all right. I'm going to move some stuff so we can see it.
We have these factored pieces. We have x plus 2, 3x minus 2, and x plus 4. And we are trying to figure out if that function is the same as the 3x cubed plus 16x squared plus 12x minus 16. Whew, that's a lot. So we have to multiply that out. So you can, if you want to, multiply these things out.
You mean like the double distribution stuff that we've been
doing?
Yeah,
you can do the double distribution. It gets a little bit messy. We've done it for you. It gets a little bit messy. If you're looking for more structure, this provides you with more structure here. So what you do is you take one of the terms, which is 3x minus 2, and one of the terms, which is x plus 2. So they took the first two terms. And then if you channel your inner, I don't know if you even had these things. They were like multiplication table-y things that if you said like 7 and 6, and you went to 7 and 6 and you pressed it down and it told you what the answer was. Did you have one of those, Mr. Carlson?
Nope.
Oh, so the humans may not know what I'm talking about, but it was a pretty cool little thing.
In middle school, you would have called this an area model for multiplication.
Yes. So you're doing 3x times x, which is 3x squared, 3x times 2, which is 6x, negative 2 times x, which is negative 2x, and then negative 2 times 2, which is negative 4. And then they combined the terms in here that were alike.
So I
and the negative 2. And that gets 4x. And that's where they got this quadratic right there. And then they did the same thing, multiplied each of the terms, 3x squared times x, etc. I'm not going to say them all because you might go crazy.
So the first one multiplied those two pieces together, and then the second box added that piece to multiply together as well. Oof.
Yes. Now, the questions that they're asking us are, how can you use graphing technology to verify? You did this with the pattern section of your quizzes at the beginning of the year. You just put the two functions in right up there. And if they show up as overlapping functions on Desmos, oh, we're talking about the same thing. So that's a way you can support yourself. So if you don't get to the same answer, you should be like, I might have made a distribution error somewhere. So if this structure helps you, use this structure.
All right, so we have to determine these things algebraically. This looks like another place that it might be a good idea to pause for a second and try these on your own, and then take a look at what we did and as far as final answer.
And I think we'll show you two different structures, but give it a shot, pause it, give it a shot. We believe in you. And then we can go for it. So if I'm looking at, oopsies, I'm on the wrong thing, so I moved the work you did. If I'm looking at the first two here, if I use that structure idea that they had, if I have x and 2, and then I had negative 3x and 2, negative 3x times x is negative 3x squared. 2 times x is 2x. Negative 3x times 2 is negative 6x. And 2 times 2 is 4. So that's going to give me negative 3x squared. Negative 6x and 2x is negative 4x. plus 4. And now Mr. Carlson's building this lovely little box. Love it. So you're going to put negative 3x squared, negative 4x, and 4. And if you have caught up now and you understand what's going on, you should pause us and you should work to finish it to see if you can get to the answer we're going to get to. That would be a very good student move. If you were confused at the beginning, but now you're like, oh, I know what's going on, pause the video and now do the work and then come back to us. But I'm just going to continue pretending that you did that good student move. 2x times negative 3x squared is negative 6x cubed. 2x times negative 4x is negative 8x squared. I wrote a squared there, that should be a cubed. And then 4 times 2x is 8x. And then negative 3x squared times 1 is negative 3x squared. Oh, these are just going to be negative 4x and 4 because we're multiplying by 1. So I don't have to work hard on those. Oh, Mr. Carlson, what are you doing?
I was combining like terms to save you a little bit of time. I noticed that as you were multiplying things out, they happen to line up on the diagonal. So it was pretty easy for me to see, okay, that those two are going to add together. Negative 3 plus negative 8 is negative 11. Those two are going to add together. Negative 4 plus 8 is 4. And the ones at the beginning and the end kind of were stuck on their own. And they line up on the diagonal because of the way that we ordered the multiplication, going from highest degree to lowest degree. So just be careful if you're going to use some hints like that. That's a little bit similar to something called lattice multiplication, which some of you may have learned when you started multiplying numbers together.
And I actually don't like the graphs they gave us on the right. So I'm going to get rid of them, but I'm going to look at that question first. How do the factors of the given expression relate to the zeros of the graph? So keep that in mind, but I'm getting rid of those graphs. And here is why I don't like that graph. I want this graph. It has nothing on it. The other one had too many lines. It was too confusing because I don't care about the specifics. I care about a sketch. So if I look at that first one, I got x plus 2 equals 0. I forgot the 2. So that's going to be x is negative 2. So I'll put negative 2 here. I have negative 3x plus 2 equals 0. Subtract the 2, divide by negative 3. That will be 2/3. And then
It's a scary fraction.
Right. And so that's why, like, why give me all that information with the lines and all that stuff? Just give me the blank graph so I can say, okay, I'm going to put 2/3 here. Sounds good. I don't have to freak out about it. I can just put it down. And then I've got 2x plus 1 equals 0. Subtract the 1, divide by 2, you get negative 1/2. And really, I should have waited to graph until the end in case I messed up the location of pieces. But I kind of had an idea where we were going. So now I've got negative 2 for a 0, negative 1/2 for a 0, and 2/3 for a 0. You can go through and figure out how to graph all of the various regions. That would be a good thing for you to be doing. If you want a hint, I'll give you a hint. X plus 2 is going to look like that. Negative 3x plus 2 is going to look like that. And 2x plus 1 is going to look like that, something like that.
Do the exact slopes actually matter for this, or just where they hit the x-axis?
Just where they hit the x-axis. So all I did was I knew which one hit the x-axis where, and so then I knew like x plus 2 had a positive slope, and negative 3x plus 2 had a negative slope, because really that one should be steeper. That was a bad graph on my part. And then 2x plus 1 has a positive slope, but steeper than the blue one. So if you need to use that to support you, you should see you have 2 negative pieces over here, and then a positive piece. So if I do a negative times a negative times a positive, I get a positive. So this graph, which we've been doing in yellow, must come from positive land. And then I have a positive times a positive times a negative. So that means the graph has to be negative. These are all positive, so we got to go positive. And then 2 positives and a negative times a negative is negative. So we're going to go positive to negative to positive to negative, which is similar to one of the shapes that Mr. Carlson mentioned on the previous page.
Yeah, that looks like it's kind of like flipped upside down for that, the one that we looked at, which is okay, and there's a reason for that.
And I'm hoping they're saying, wait, we had parabolas, and we had concave up and concave down parabolas. What made those that? And what here might be making things different. That would be a good thinking thing for you to be doing.
Cool. Do we want to leave B for them?
Yeah, I
Since
would say
that's
try B out, put it into Desmos at the end and see if you get there.
Yeah.
If I put it into Desmos, I would put in x plus 2 into Desmos, 5x plus 1 into Desmos, and then the product. And actually, I would do both products. So I would do x plus 2 times 5x plus 1, and then I would put whatever you get as a product and see if it matches your sketch. Mr. Carlson's naming them if you'd like names.
I'm just doing that because I want to remind you that in Desmos, if you name a function and then use the name, it will graph based on that. So if you have f of x and g of x, instead of having to rewrite those separately, you can do f of x times g of x, and that's okay. This is really useful for kind of big functions that are annoying to write out. Maybe not for this one because these are pretty short. But cool.
I think for C, they can do the same thing. They can do that. We're going to have confidence in them. For D, I think we might need a little support.
Would it make sense to give some support by suggesting that, oh man, something cubed means that we're looking at multiplying that by itself 3 times? So rewriting this might be really helpful as x plus 2 times x plus 2 times x plus 2. Do we think
it would? And actually, I just cheated and looked at the next page. I think we can just go to the next page. Like, try these by all means. Not my humans at home. But if we go to the next page, they're actually breaking this problem down a little bit.
Ooh, I like this. So this idea that x plus 2 cubed is the same as x cubed plus 8. First of all, we know that Max is wrong because we can see the thumbs down. Second of all, if you read the question, it says Max is incorrect. So hopefully we have this double hit of, okay, this is not correct. By the way, this is a mistake that Mr. Butterworth and I see with students all the way up through the highest math classes that we teach, in terms of like classes that students take senior year and get college credit for. Our brains are not good at remembering that this doesn't work for whatever reason that is. So it's okay to make some mistakes as long as we look at this and we're like, oh yeah, nope, I need to kind of think about this a little bit more. Okay, so we talked about this was the same as x plus 2 times x plus 2 times x plus 2. Would it make sense if we use the same type of model that we used before to multiply this out?
I think so.
And if we do x plus 2 and x plus 2, we get x squared plus 2x plus 2x plus 4. And you might already see what Max is missing here. 2x plus 2x is 4x. That if we just did x plus 2 times itself squared, Max would have gotten x squared plus 4. And we got x squared plus 4x plus 4. So then
Mr. Carlson he did something that might have blown some brains up just now, and I don't think he even noticed that he did it. Notice how his box does not include all of the pieces. He has 2 sets outside. If that freaks you out, you can just box it in, because that's how they had it on the previous pages. But it kind of makes it a little more confusing to remember to do that. So it's okay if you write it the way Mr. Carlson is. That's totally fine, to ignore kind of those outer boxes. But again, if you need that structure, if you want that structure, by all means, go for it. So now he's multiplying those pieces. He did x squared times x is x cubed. 2 times x squared is 2x squared. 4x times x is 4x squared. 4x times 2 is 8x. 4 times x is 4x. 4 times 2 is 8.
Now I am combining some like terms. X cubed plus 6x squared plus 12x and then plus 8. That's very different from what Max had, although Max had the beginning and ending piece, which was the x cubed, and 2 cubed is 8. It's the middle stuff that's missing from that. And that's the danger of trying to, as we say, distribute an exponent like that, which you can't do.
Because of the addition sign. If that was the multiplication sign, different rules.
Yep.
So we're supposed to determine how many x-intercepts does the function have. I feel like we can go from your top piece right there. And we can say 3. It's got to have 3 x-intercepts. If you're hearing a dog, by the way, it's a dog outside of my house now that is barking. So we've got to have 3 x-intercepts. And then the multiplicity, how many zeros? Oh, this is interesting. So how many zeros? I'm going to change what I said. I'm going to say 1 x-intercept.
Yeah, I was going to say
3 times because I didn't read ahead about what they were asking me. 3 times. So we have 1 x-intercept because x plus 2, x plus 2, and x plus 2, if we set each of those equal to 0, we will get the same number. So we have 1 distinct x-intercepts. It happens 3 times. So the zeros, we have 3 zeros. In the ones, well, how do I?
1 0 multiplicity 3.
They're messing me up with the wording here.
Yeah.
1 0 multiplicity 3. There we go. I got that.
So it's like saying that we have 3 zeros, but all 3 are the same 0.
Right. I think I would prefer that to say how many distinct zeros do we have?
I would too.
We have 1 distinct 0 happens 3 times. Technically, we have 3 zeros. They're just all the same 0.
Yeah, that kind of bothers me a little bit, but that's okay.
And that's all we have for you.
Yeah.
We did everything, Mr. Carlson.
We did. Wonderful.